Hello everyone. Today we are going to discuss about physical significance of wave function psi. Let's have introduction. Fundamental particle such as electron may be described as particle or wave. Electron may be described using a wave function. The wave function symbol is a Greek letter psi. The wave function psi is a mathematical expression. It carries crucial information about the electron it is associated with. From the wave function, we obtained electron's energy, angular momentum, quantum number, etc. In 1926, Erwin Schrödinger deduced the wave function for the simplest of all atom, hydrogen. Solving the Schrödinger equation enables scientists to determine the wave function for electron in atom and molecule. In addition to importance of psi, psi square also have enormous significance. Psi square is the probability density. It tells us where the electron is most likely to be found in the space around the nucleus. There is 100% probability that electron is somewhere. In other words, a probability is 1. In this diagram, we can show on y-axis we are showing probability density psi square. On x-axis, we are showing the electron distance from the nucleus. The curve is showing the probability of existence of the electron. The peak is showing the maximum probability of electron in this particular area. Now let's discuss about some important definition and formula which we will need in future lecture. So first, wave number. It is propagation number or angular wave number is represented by k. The definition is number of wavelength per unit distance. It is a scalar quantity represented as k is equal to 1 upon lambda. Wave number equation. It is number of complete cycle of wave over its wavelength. Equation is k is equal to 2 pi by lambda, which can also be written as k is equal to 2 pi nu upon Vp, which is equal to omega upon Vp. Vp is the phase velocity of the wave, omega angular frequency. In matter wave, k, that is wave number, can be written as p upon h cross, which is equal to under root of twice me upon h cross, where E is kinetic energy of particle, m mass of particle, p momentum of particle. H cross is equal to h upon 2 pi, which is also called as reduced Planck's constant. Now according to Planck's quantum theory of radiation, energy of photon of frequency nu can be written as E is equal to h nu. Photon with effective mass m, if we are considering, then according to Einstein mass energy relation, the energy is written as E is equal to mc square. Comparing this equation, we will get lambda is equal to h upon p, which is nothing but de Broglie's wavelength. Now we are going to start with physical significance of wave function psi rt. Rt is representing space coordinate as well as time coordinate. Wave function is complex quantity. It has no physical meaning. Wave function is expressed in form of complex quantity psi xyzt is equal to a plus ib, where a and b are real function of variables x, y, z and t. The complex conjugate of equation number 1 can be written as psi star xyzt is equal to a minus ib. Now multiplying equation 1 and 2 will get mod of psi xyzt whole square. As we discussed in slide number 2, it is nothing but probability density. Now let's define it. What is probability density? According to Max Born, the probability that particle will be found in a defined volume element dV surrounding the particle at position x, y, z at any time t is given by P dV is equal to mod of psi x, y, z t whole square dV. Now, probability to find the particle in a defined space is directly proportional to integral of psi x t whole square over the volume. Here psi of xt we considered the one-dimensional wave function. In this point it is given that if we want to find the probability in some particular area, then we have to integrate it over that particular volume. Now motion of particle in 1D. In 1D case, the probability is given as P dx is equal to psi xt, psi star xt dx, which can be written as mod of psi xt whole square dx. Total probability of finding particle over all space in one dimension can be written as P is equal to integration minus infinity to infinity mod of psi xt whole square dx. This we can apply for the 3-dimension space. So in 3-dimension space, probability P is equal to minus integration of minus infinity to infinity mod of psi xyzt whole square dv, where dv is volume element dx, dy, dz. Let's discuss about very important property of wave function. So let's start with normalization of wave function, which is also called as normalization condition. So if wave function psi mrt is multiplied with its complex conjugate psi m star rt and integrate it over whole volume is equal to unity, it can be written as integration minus infinity to infinity psi m rt psi m star rt dv is equal to 1. If the result is 1, then we can say that this wave function psi m rt is normalized wave function. Now let's move to next property, orthogonalization of wave function, which is also called as orthogonal condition. If wave function psi m rt is multiplied with other complex conjugate psi n star rt and integrate it over whole volume and it vanishes, so mathematically it can be written as integration minus infinity to infinity psi m rt psi n star rt dv is equal to 0. Now if the result vanishes, means is equal to 0, then both these wave functions psi m and psi n are called as orthogonal wave function. Here make it clear that both these wave functions are different, so we have written n is not equal to m. Now let's move to another important property, that is expectation value. What is expectation value? To correlate the result of experiment with the theory, the expectation value of any parameter is given as expectation value q is equal to integration minus infinity to infinity psi star q psi dx upon integration of minus infinity to infinity psi star psi dx. We are going to explain here. If we want to find out the expectation value of any physical quantity, here in place of q we can consider any physical quantity such as momentum, position of that particular particle. So we can find out the expectation value or the expected value of that physical quantity with this result. So let's apply it for position. So expectation value of position is given as integration of minus infinity to infinity x mod of psi square dx upon integration minus infinity to infinity mod of psi square dx. It can be also observed like expectation value of x minus infinity to infinity psi star x psi dx upon integration minus infinity to infinity psi star psi dx. Now consider the denominator of this equation. If the wave functions are normalized, then the denominator will turn out to be, the result of the denominator will turn out to be unity, and we can write this expectation value as expectation value x is equal to minus infinity to infinity psi star psi x psi dx. Now we are going to discuss about probability of finding the particle in given limits. It means if limits are provided, how to find out the probability. So probability between given limits x1 and x2. Here we are going to take one dimension case, is given as p is equal to integration x1 x2 mod of psi xt whole square dx. So we have completed the physical significance of wave function psi. Now in this slide we have to understand how we are going to write the wave function psi mathematically. So for this we have to consider some basic points. As we know that the varying quantity characterizing the matter wave is denoted by psi xyz at a point. Wave function is also called as wave amplitude. Complex quantity wave function psi rt is defined to describe entire physical state of particle or system of particles such as atom or molecule. Psi, now how to represent psi? Psi rt, which is a three-dimension function which can also be written as psi xyzt. It is a three-dimension wave function. Psi xt, psi yt, psi zt are the one-dimension function. Now let's talk about wave function in x direction. Wave function in x direction can be written as psi xt is equal to a exponential of minus I omega t minus x upon v, where I is equal to root of minus 1. Here phase velocity is the velocity with which the wave packet is propagating. So v is nu lambda, which can also be written as omega upon k, and here the wave number k can be written as omega upon v. Now this wave function equation can be written in different formats, which is given here. In above equation, just we are going to multiply the omega in the bracket, so we'll get psi xt a exponential of minus I omega t minus omega x upon v. Here omega upon v can be replaced by k. Now in this equation we are going to multiply and divide by h cross. Again we will get the new form of the wave function psi, that is psi xt is equal to a exponential minus I upon h cross et minus px. All these equations are just in different form of wave function. We have to select the wave function as we need. Now again let's discuss about how we are able to define this wave function. Now we have to move to the classical mechanics. In classical mechanics we have discussed about the displacement equation y xt is equal to a sine kt minus omega t plus phi. Here all these physical quantities are defined, that is y is representing what position, that A is representing amplitude, K is representing angular wave number, omega is representing angular frequency, T is representing the time, X is representing the horizontal position, and phi is representing the position. In the same manner as we have discussed earlier in classical mechanics, we can also define the wave function for the material particle. So in this way we have completed the physical significance of wave function phi. Thank you.